So we were conducting for many, many years high altitude medical examinations and performed expedition planning. So here you can see I am wearing a Nautilus system in Iceland. So we went ski touring in Iceland. And there are many different things that you can actually investigate. So first of all, I will tell you some FAQs. When you're doing a trekking tour, ski tour, I will show you some results about pulse oximetry. I show you how to calculate heart rate variability, how to assemble EEG electrodes, how to calculate and run ERD experiments. And then I have examples of running experiments at Dachstein, that's a mountain in Austria. And then we did also measurements in Pakistan, Germany, on Kilimanjaro, and also in Nepal. And I will show you some of the results. So if you Google for the top 10 once in a lifetime trips, then you can find, for example, a champagne flight to the North Pole, but you can also find a trek to Mount Everest Base Camp. And this is actually where we used our G.Mobilab system to record EEG data during the trekking tour and to investigate the effects of high altitude on the human body and on the brain. So if you need or if you book a climbing tour to Mount Everest, you can actually see that the permit costs are pretty high. So Mount Everest costs around 50,000 US dollars, but you can bring 7 of your friends. And then there are more peaks above 8,000 meters, which are cheaper, so around $10,000. And in Nepal, they have also peaks between 7,500, 8,000 meters. They are costing 3,000 US dollars for 7 members. And then they have so-called trekking peaks. So they range between 6,500 and 7,000 meters. They're much cheaper, between 1,500 to 2,000 US dollars. So if you divide it by 7, it's actually not so expensive anymore. So if you're going to such an expedition or a trekking tour, you have to investigate a couple of things. For example, what should you do if you get sick during the trek? So with high altitude, it's more likely that you get a cold, that you start to cough, you get a headache, you maybe get high altitude sickness. And you have to be aware that you have to do something against it. And very often helicopters cannot reach the height. So it's, for example, good to take a physician with you. So what happens if I feel unwell while trekking? So it's good to take some medicine with you. What happens if I get injured? Do I have a cell phone to call a helicopter? What kind of accommodation can I expect? Do you carry your own tents? Do you sleep in mountain huts? Whatever you can find over there. Is altitude sickness an issue? So altitude sickness mostly occurs if people sleep higher than 3,500 meters the first time. Then the chances are already pretty big that you get a headache or that you vomit because of the high altitude. And if you go beyond that, then of course it's even worse. So which meals do you get during the trek? Should you cook yourself? Can you buy something to eat? Or maybe you have to carry everything yourself. And then you also have to solve the question, who carries it? So if the trek is maybe for 4 weeks, it sums up to quite a heavy backpack. How cold is it? So in Nepal, for example, during the day, it's pretty comfortable. But if the sun drops down, then it gets tremendously cold. Then you need a very good sleeping bag. Will I be able to stay in touch with home? So in Nepal, they have, for example, internet cafes, so you can send something home, but maybe you also need the satellite telephone for rescue or to communicate. And of course, how much money do you need? Because very often they don't have ATMs, so you're not getting money over there. If you have to pay, for example, the helicopter for the rescue. Then how physically demanding is the trek? So can you do it? You know, if it's maybe 2 hours a day or maybe 16 hours a day. What do I need to carry during the trek? You need, of course, warm clothes, but you need also the medical equipment. So the brain-computer interface, the EEG systems. And they should also be lightweight because you don't want to carry a heavy backpack. Is there package weight limit on domestic flights or international flights? So very often they use very small airplanes and you cannot really carry much. And the big problem is nowadays also with the batteries. So these lithium ion batteries are very dangerous and very often they are not allowed on flights. And then you have to find a solution how to carry them. Or if you go with an avalanche airbag, they have this cylinder inside with the pressure gas. And in the US, for example, you're not allowed to fly with that. So you have to empty it before. And then you are maybe in the mountains and you have to refill again, but it's not so easy to find a refilling station. Then is the trek considered safe? If you go to Russia, for example, to the Caucasus, it's maybe not so safe at the moment. Then do you need a climbing permit? Is there somebody controlling the climbing permits? And maybe they turn you around because you are not allowed to do it. Is the team covered by insurance? Very important. So a helicopter rescue in the Alps is costing about 8,000 euros. So maybe it's good to be a member of an Alpine club to pay for the rescue. And is it also safe to drink the water over there, or do you need maybe chloride to prepare it? Then energy is, of course, a big problem when you're on an expedition. So people are carrying, for example, such portable battery supplies. But then you also have to carry the fuel to run the energy production for recharging your computers, for your cell phones, and so on. And you also have to consider that it can get very cold, -20, -40 degrees. And then the question is also if they are still operating. And of course, with accumulators, low temperature is a big problem because the energy becomes less and less with dropping temperature. So you need a solution that works also under very cold conditions. Here you can see one of these devices. It's a pulse oximeter, which works with normal batteries. And you can just stick it on the finger and then it gives you the oxygen saturation in your blood between 50 and 100%. It is very nice for group studies if you're doing high altitude research, but it's also nice if you're mountaineering yourself to monitor where your oxygen saturation is located. You can see the numbers are given here. So 99, 198 is normal, but if it drops down, then it gets pretty quickly dangerous. And then you can get high altitude sickness. So Markus Tannheimer from the German Bundeswehr, so that's the army in Germany, is, for example, a physician, and he's doing a lot of these testings. And here you can see also the fluctuations of the pulse oxygenation when you are measuring on the finger. So this is done over 3 hours. And you can see it goes from 58 maybe up to 75. So you need a couple of different measurement points to get a solid value. And last year we were, for example, in Switzerland ski touring, and in the hotel, which was at 2,000 meters height, so not so high, a little girl, 15 years old, suddenly felt really bad. She was vomiting and everybody believed she is ill. And then she had a little watch that told her actually that her oxygen saturation was 68. Then a helicopter was coming to pick her up and bring her to the hospital. So this pulse oximetry is also used in mines in South America because they're also high up. And it's just very dangerous that the saturation drops down and people get sick and they can also die because of that. And if you're on an expedition and you are very high up and your oxygen is really low, you have a headache, you vomit, then these are all very dangerous signs. But maybe it's during the night and you cannot really escape because you're locked in your tent high up on the mountain. And then you can also do something against it, and that's called auto PEEP respiration. So in this case, you have to exhale with closed lips for 8 seconds, so very slowly. And then you inhale within 2 seconds pretty quickly. And if you're doing this for 30 minutes, then you can increase, for example, the oxygen saturation, like shown here in the diagram, from around 62% to about 90%. And then you can see also it stays for about 90 minutes. or even longer, 3 hours in this case. And then you have to do it again. So this is an emergency respiration strategy that helps you to survive a night. It's also very useful to have this knowledge because you can also tell other people to investigate it. And Markus Tannheimer did also very nice experiments on the Refugio Turin. This is very close to Mont Blanc. And this refugio is very high up, 3,371 meters. And there's a cable car going up. And then there's a stairway, which is 90 meters long. And the height difference is 46 meters. So you are going from Italy all the way with the cable car to the top station, and then you have to do the stairway. And when people reach the hut, they are completely exhausted because the body is not used to this high altitude and it cannot really deal with the low oxygen in the Alps here in this case. And this is a very nice testing bed that he's using for the German army. So the soldiers have to run as quick as possible, and he's just investigating the oxygen saturation, and that's a very good marker if they're actually getting ill doing the expedition or to the mountaineering what they have. So beside oxygen saturation, a very good marker is also heart rate variability. So this is the variation of the heartbeat. And there are many publications about it. It's used for many, many years. And here's an example of a Valsalva maneuver. So this is more or less a tilt table. This means a person was just lying on the table, was recorded, as you can see here, for a couple of heartbeats. This is like 10 minutes. So average heart rate was around 55 beats. And then the table was flipped up. And suddenly you can see that the heart rate goes up to around 80 beats per minute because the heart has to do more. It has to pump the blood into the body. And for that, you need a higher heart rate. And when you are calculating the heart rate, then you're trying to find the QS complex in the ECG, indicated here with the marker, and the distance from one QS complex to the next one is just the RR interval, or also the heart rate in beats per minute. And you can describe the heart rate variability, so the changes of these RR intervals, with different measures. And in the literature, they have time domain measures. So this means you are just measuring the different intervals, and then you can look, for example, at the mean RR interval, which is, for example, 1 second if you are having 60 beats per minute. Then you can look at the minimum RR interval, at the maximum. You can look at the difference between the minimum and the maximum. You can look at the difference between night and day, but you can also look at the difference between the bottom sea level of a mountain and the top of a mountain. And then there are also complex time domain measures. You can calculate, for example, the standard deviation of this RR interval. So you can calculate first the variance of the RR interval and then the square root. So they are all useful for different applications, but it's very important that you compare the same recording lengths. So if you're doing on sea level 5 minutes, then you should also do in the high camp 5 minutes. Or if you want to do it on a daily basis, you can also calculate it over 24 hours, but then you have to also compare it to 24 hours. And then there are also segmented measures. So in this case, you are looking at the distance between the RR intervals, and then you are calculating the standard deviation, or you are doing first the standard deviation and then the mean. You can also count or calculate the difference from one RR interval to the next one. And this is the RMSST, the square root of mean squared differences of successive NN intervals. And that's a very nice parameter that we used very often for the high altitude mountaineering, because it's very easy to calculate and it's just showing very nicely what's going on. Then the NN50 is just counting the beats that differ by more than 50 milliseconds. That's also a very good measure. Because you see effects, high altitude effects immediately. But keep in mind, segments must be equally long. Of course, if you're counting how many beats are differing, it doesn't make sense if you have not equal lengths of the intervals. You can also calculate the ratio. So PNN50 is just the NN50, the intervals that differ by more than 50 milliseconds, divided by the total number of heartbeats that you're having. Yeah, I dropped that. For the tilt table experiment, I can show you some results of the time domain measures. This is just some basic background so that you can interpret the heart rate variability outcome during mountaineering. So here you can see the person is at rest, lying on the table. Mean RR interval is 1.1 seconds. And let's pick, for example, the mean heart rate 53 beats per minute. If you look at the person when the table is lifted up, you can see the mean heart rate went up to 77 beats per minute, so much higher. And then we can also look at the histogram. You can see here the heart rate when the person is lying is much lower compared to the time point when the person is tilted up. And you can also see that the IMSST, so the heart rate variability measure, is here 60 and here 16. So during the task, when the person is tilted up, the heart rate variability drops down. And this shows that the body is more stressed, the heart has more to do. And if you look at the PNN50, so the number of intervals that differ by more than 50 milliseconds, then we can see here that we have 47%. So it's a very high heart rate variability. This is considered to be healthy. And when the person is tilted up, so there's actually not much movement from lying to standing, it drops immediately down to 0.7%, so almost nothing. And this shows the stress to the heart by this tilt table experiment. And then there are also frequency domain measures. So you can either calculate the fast Fourier transformation, or you can use an adaptive autoregressive model, a parametric method for doing it. So normally these parametric methods give you a smoother signal, and that's also the reason why it's very often used. And then there are different frequency bands of this spectral analysis. So the ultra low frequency, the very low frequency. The low frequency is an important one. So this is between 0.05 and 0.15 Hertz. And this is considered to represent sympathetic nerve activity. And the high frequency band, just above, is considered to represent parasympathetic nerve activity. And these are two important markers, again, for high altitude medicine, or in general, how much your heart is under stress. And of course, you can also calculate the ratio, LF over HF. So if the ratio is 1, this means LF and HF are in balance. This means the sympathetic and the parasympathetic system of the autonomous nervous system are in balance. This is normally when you're not stressed, when you are relaxed, when you are sleeping. And here for the tilt table experiment again, so during rest, you can see here the LF component, sympathetic, here parasympathetic. You can see they have almost the same size. This guy is a little bit smaller. Ratio is 1.1, so almost 1. When the person is tilted up, you can see only the LF component is there. The HF component disappeared. So it's fully sympathetic driven because the heart has to pump immediately blood into your legs and into the body, and sympathetic activity increases. And here you can see the LF to HF ratio 7. So the sympathetic system is 7 times more active than the parasympathetic one. This can also be visualized in a heart rate variability power spectral density block. So here is the tilt table experiment. At the beginning, the person was just lying down. This is sympathetic activity, parasympathetic activity, and as soon as the person is flipped up, you can see parasympathetic disappears completely and the sympathetic system gets much stronger. So much to the background. You can also look at heart rate variability for different pathologies. So if somebody has a heart infarction, then you can see the heart rate variability is very small. Parasympathetic activity goes completely down. Sympathetic activity goes very up, a lot up. For heart transplantation, heart rate variability doesn't exist anymore, for example. Also interesting. And then you can also look for tetraplegic patients and so on. And another interesting parameter is, of course, the EEG for high altitude medicine, because we want to understand how much the lack of oxygen is affecting alpha and beta. And for that, we use the simple 10-20 system for assembling the electrodes. So we put electrodes around C3 and C4, the left and the right hand representation area. That's an image from Günther Edlinger, my co-founder, when we were working in Gerd Purcell's lab. And you can see here the red spot, the event-related desynchronization on the right hemisphere, if the person does a left-hand movement, and contralateral for the right-hand movement. And we place the electrodes here around C3, C4 to capture exactly these movements. This is just overlaid to MRI data so that you can see the central sulcus and understand better where left hand and right hand, and also foot, are represented. And the event-related desynchronization is basically calculated by bandpass filtering the data, for example, in the alpha range. Then you are squaring the EEG, you are averaging the trials, and this gives you the ERD. This is actually what Gerd Purceller described during his work at the university about 50 years ago. And this is the basis for ERD and the EAS concept. And when a person is actually moving the finger, actually here at second number 2, then afterwards you can see the red spot. So Purceller always plotted ERD in red. This means the amplitude goes down. And when the movement terminates, then you get the beta rebound. So this is actually an increase of activation. And he made a lot of publications with ERDs and beta rebounds. So just look up his papers. And this is something that we investigated on Dachstein. This is a very nice mountain here in Austria. It's about 3,000 meters high. They have a cable car which goes from the base station to the top station within 6 minutes. So you can also climb it yourself. This is the trail actually to the top station of the cable car. It's actually located here. And so for the study, we used at this time the G-Mobile app. This was the first wireless and portable EEG system actually on the market. It used AA batteries. This was very nice because even under cold temperature, it was still working. And then we needed, of course, some background. So at sea level, the oxygen concentration is 21%, but the partial oxygen pressure is 760 millimeter Hg. On Dachstein, it's about 550, and on Mont Blanc, which is 5,800 meters high, it's about half of it, 380 millimeter Hg. And this is pretty fascinating. So at a relatively low altitude, only half of the oxygen partial pressure is still existing. And this means your brain is actually getting much less oxygen. Of course, also your body, but we wanted to investigate how the brain and the heart are actually reacting to that. And for that, we needed a task, a very concrete task that the persons were doing at the base station and on the top of the mountain. And for that, we had a finger tapping test. So you can see the measurements were done at 2,700 meters. This was the top station. Bottom station of the cable car was 1,700 meters, so height difference of about 1,000 meters. And the cable car took it in 6 minutes, which is quite fast. This was our paradigm. So we had just the green and the red light. And if the green light flashed the button, the person had to press as quick as possible the button. So it was a reaction time task because we also wanted to look at reaction times, but we wanted to inspect the sensory motor cortex, how difficult it is at higher altitudes to do the finger pressing. This is our mobile lab. So we were coming out 2002 with the mobile lab. We connected the EEG electrodes, and we could also record ECG and heart rate variability with the device. So here you can actually see the recording situation in the cable car. At this time, pocket PCs were used for recording. So the mobile lab was just plugged in here. And here you can already see the EEG coming from the left and the right hemisphere. That's the ECG. And here you can see the trigger markers when the person was pressing the button. And here you can see from the base station to the top station how the heart rate actually goes up. Person started with 85 beats. On top, the person had around 98 beats per minute. But remember, the person was just sitting in the cable car. And the only difference is that the cable car stopped 1000 meters higher up. And this is the event-related desynchronization and also the beta rebound that we are actually expecting. And then we did also the heart rate variability in time domain analysis. So I already introduced to you how this is done. And here you can already see it at the here at the base station on the bottom. You can see the heart rate for this person is around 60 beats per minute. On top of the mountain, it's 95. So the person is sitting, just doing the finger tapping test, and still we have 35 beats per minute more because the person is now 1000 meters higher. If you look at the histogram, you can see here it's a very healthy histogram, a lot of heart rate variability. On top of the mountain, it's very sharp. It's an unhealthy sign. So the heart is much more stressed. And if you look at the parasympathetic and the sympathetic system, you can see it's pretty balanced at the base station, 1000 meters high. It's completely sympathetic system driven. Again, showing the stress for the system. And then it's of course interesting to look at the event-related desynchronization. So at the base station, you can see the normal figure. We get the event-related desynchronization here when the person is moving the finger, and then it terminates with the beta rebound. And on the top station, you can basically see the ERD is the same, but the beta rebound is much smaller. And we did it in a group study with 10 subjects. So on average, you can see the heart rate goes up significantly, basically for everybody. The RMSST, the heart rate variability measure, goes dramatically down, very high p-value. And also this PNN50 goes from 10 to 0.9. So there's almost no variability anymore in the heart rate. And same for the sympathetic system. Let's look at the LF over HF ratio, goes from 2 to 4. So much higher sympathetic driven. And the ERD results can be found here. So on the base station, we have the old way of the event-related desynchronization plotting that Gerd Pfultscheller come up. So this is for one frequency range, in this case 8 to 13 Hertz. You can see we have minus 15%. For all the subjects, we have a beta rebound, very nice, plus 42%. And on the top of the station, the ERD is basically the same, but the beta rebound is much smaller. This is very interesting because it showed that this little increase of altitude is already affecting the brain. But you are not really feeling that your brain is affected when you're on top of the cable car. But with EEG technology, we can already measure that. And then we correlated also the EEG parameters with the heart rate and heart rate variability measures. You can see here in the alpha range that the EEG is very nicely correlated to all the heart rate variability measures, either positive or negative. So if the EEG alpha got up, also the heart rate increased, and it was inversely correlated or negatively correlated with the heart rate variability parameter. But very interesting, at high altitude, the correlation actually got lost in the beta range. So here you can see in alpha and beta, we have initially a very high correlation, but here in the action period, it's completely lost. And this shows again that the brain is highly affected by the altitude gain of 1000 meters. So we learned heart rate variability is completely gone. It's almost zero, completely sympathetic driven. And we can use the ERD and ERS principle to see the effect on the human brain. But this is a relatively small amplitude. Nobody is scared to be at 2,700 meters. That's the reason why we also wanted to investigate it at much higher altitudes. And for that reason, we went to Kilimanjaro, in Tanzania. We had 8 healthy people doing the experiment. Then we had the German army in Königsbruck. This is where the German Air Force is actually located. And we got 12 soldiers that were put into a hyperbaric chamber. So you can artificially elevate these guys to higher altitudes. And then we had also an expedition to Shimshal Waitorn in Pakistan, where 4 healthy people were investigated. Same paradigm. Subject was supposed to press as quick as possible after he was seeing or she was seeing the green light, the button. If the red light blinked, she was not allowed to press anything. Then we looked at the oxygen saturation, and we looked also at the Lake Louise score. That's coming from Canada, and it's a score that describes if somebody has high altitude sickness. So you have to ask 8 questions. Do you have a headache? Do you vomit? Do you feel fatigue? And so on. And it has to reach a certain score to manifest that you are affected. And then we did also a concentration performance test. It's called the D2 test. And if you look here at the first line, then you see here, for example, a D with 2 dots, and you're supposed to cross it out. Only the small d's with 2 dots should be crossed out, and you should ignore all the others. So here, for example, nothing is done. Here's another one, nothing, another one. And for every line, for every row, you get 20 seconds. And then you have to process the other one. And at the end, you're just counting how many of these items were correctly processed, how many false positives you have, and how many you overlooked. And this gives the concentration performance measure. And this is actually a very good test because it's really outperforming people, especially at high altitudes. So altogether, we looked at the EEG, at the heart rate variability, oxygen saturation, the concentration performance, and the Lake Louise test and reaction times. And here you can see the altitude profile on Kilimanjaro. So we started in Arusha. This is a nice town for doing safaris, pretty low at 1,300 meters. And then we actually hiked up all the way to Mount Meru, which is around 4,500 meters. It's a very nice peak on a volcano. And then we returned to Arusha for acclimatization. Then it took a couple of days to reach actually Mount Uhuru. This is the peak of Mount Kilimanjaro. So 5,896 meters high. Then we were more or less running down in one day, and we went to Mombasa in Kenya. So here you can see the recording situation. 2 bipolar channels, one on the left hemisphere, one on the right hemisphere. This is the push button, the mobile app for the recording. So we assembled the EEG, took a few minutes, and the experiment took like 5 minutes. And here you can see the results for the concentration performance test at sea level, at the hut after Mount Meru, and just before Kilimanjaro at 4,000 meters. And on average, you can see on sea level, we could process 242 items correctly. Then it dropped down when we reached the first time 3,500 meters. And at 4,600 meters, it was already better again because of the acclimatization effect. We can also look at the Lake Louise score. So at 0, everybody had 0, of course, no high altitude sickness. At 2,500 meters, it was already starting to go up a little bit. At 3,500 meters, it was already pretty high. Then you can see the acclimatization effect. So it dropped down again because we were on Mount Meru before, which is 4,500 meters, and then we slept lower. And this always has a very good impact on the human body. So you should sleep lower than you hiked up so that your body adapts to the altitude. And then you can see when we just on the night before Kilimanjaro, it was going up again because we were at 4,600 meters. If you look at oxygen saturation at sea level, it's normal 97%. At 2,500 meters, it's a little bit lower. at 3,500 meters. This is pretty high, where many people already get the high altitude sickness. It's already below 90. That's the first warning sign. And then you can see the acclimatization effect. So we went up high to Mount Meru and came back. Very good for acclimatization. And then it drops down again shortly before Kilimanjaro. 80 is already pretty low. And if you look at the heart rate, again, 71 on average, then it goes up to even 99. So people were just sitting in the tent with 100 beats per minute, not doing anything. This is just the altitude that's highly affecting the human body. Then the acclimatization effect shows that the heart rate goes down. And of course, it was lowest again, or very low, just before Kilimanjaro because it's so high. And this is also on an individual level. So we had 8 people. And interesting is, for example, subject number 4. You can see here the Lake Louise score goes up to 2 shortly before Kilimanjaro, even 3. So this person wasn't able to make Kilimanjaro because he felt really sick. But if we look at this oxygen saturation, then you can see 97, 97, 90, not so small. 90, 86, again, not so small. So just by observing the oxygen saturation, we wouldn't know that this person has high altitude sickness. So you need a couple of other parameters to figure it out. If you look at the heart rate, you can also see here it goes up from 62. This is a very good value, actually. 75, and also in the high camp, it's 78, not so high. Actually, this person had, for example, a much higher one, or this one, 115, but this person didn't get ill. Then we went to Pakistan to climb Shimshal Whitehorn. This was actually done by Markus Dannheimer. And you can see they started in Islamabad, then they went to Gilgit, and this is where the trekking actually started. They did the first measurement at 2,500 meters, then they climbed the peak, slept at 3,100 meters, then they climbed another peak, 5,366 meters. This peak was actually climbed by the team the first time, returned to the base camp again, 3,100 meters. They climbed the Sunrise Peak, 5,500 meters, returned to the base camp. Then they made a high camp. That's measurement time 0.5. They climbed the Whitehorn. It's a little bit above 6,000 meters. And they returned back to base camp and actually finally went to Islamabad. This is the recording situation. In the background, you can actually see the Whitehorn. It's a very nice mountain in Pakistan. Here you can see the Mobilab. That's Markus Dannheimer from the German army. He is actually a physician, very active in high altitude medicine. And at the moment, he's just pressing the button. Now here you can see the results. So you can see how the altitude increased from Gilgit all the way to base camp. There are a couple of measurement time points in base camp, the high camp, then they climbed the Whitehorn and they returned to base camp. You can see the German army is pretty nicely trained. They have a low, medium heart rate, 66 beats. And then in high camp, it even dropped down, didn't affect these guys much because they had already an acclimatization tour before to 5,400 meters. So this is boosting the hemoglobin production in the body. And that's the reason why the heart rate already dropped when they reached high camp. So acclimatization tours to high altitudes are actually very good, but you have to sleep lower so that the body can adapt. Then they did another acclimatization tour, slept again at high camp, and then they climbed Whitehorn. And you can see the heart rate after Whitehorn because of the acclimatization is also pretty nice. Heart rate variability is really high. First time at high camp because of the acclimatization. Then at the high camp, it reaches the minimum because they are not used to the high altitude. They slept there. That's always very difficult for the body. And after the climb of Whitehorn, we are reaching actually the minimum. Can also look at LF, sympathetic versus parasympathetic activity. You can see it's pretty low, so here it's high. Yeah, pretty nice. And then we did experiments in a hypobaric chamber. So people were put into the chamber, equipped with the EEG system, with the ECG system. So they had everything with them. Then we were bringing them up to altitude with 5 meters per second. So within 1 hour, they reached actually 4,000 meters. This is highly demanding for the human body to go from sea level to 4,000 meters within 1 hour. Of course, they were not doing it. They were just sitting there and the oxygen pressure was reduced. And then they slept in the hypobaric chamber. This is our first measurement time point after the night. And then we had also a measurement time point when they returned to sea level. This is the recording situation, so they have comfortable chairs inside the chamber. Here you can see the pocket PC that we used for the recording, the push button, the EEG system. And when we compare now the different recording sites, then we can see on Dachstein, the heart rate increased from 69 to 80, from the base station to the top station. Sympathetic to parasympathetic activity was 2.1. At high altitude, it's about doubled. The altitude that we finally reached was 2,700 meters within 6 minutes. So this was a very fast ascent. If we compare to Königsbrück, so where we had 11 hours at 4,000 meters altitude, you can see the heart rate increase is very similar. And also the sympathetic to parasympathetic ratio is very similar. It's about doubled. But people had 11 hours to adapt. On Kilimanjaro, you can see the increase of heart rate is similar. And also the increase of the parasympathetic activity is similar, a little bit less, but we had 8 days for the acclimatization. And in Pakistan, it's of course the highest altitude gain. Heart rate increase is similar. Sympathetic increase is similar. Altitude is high, but they had 16 days for the acclimatization. And this is just super important. So if you take your time for the acclimatization, you stay healthy. And this science that we are doing here helps to find nice strategies for the for mountaineering. Then we climbed also Shulu far west in Nepal. And if you look at Nepal here, so we have also people from Nepal in spring school, then you find Kathmandu here. That's the Everest region where Mount Everest is located. That's the Annapurna region. And just in the background, you can see the Shulu far west. So it has a lot of glaciers, very nice. And here you can see an overview of all the trekking peaks in Nepal. I think they have like 20 of them. And we were actually going to the Shulu group, which is just in the south of Tibet. This is actually the entrance to Mustang that some people might know. Here you can see the eternity that we had. So we were 22 days on the trek. We were flying to Kathmandu and stayed in Kathmandu. Then we went by bus to Beji Shahar. This is 800 meters. It's pretty tropical and hot. They even have cobras over there. And then we went all the way to Manang. That's a very nice village at 3,300 meters. Over there, we stopped a little bit for acclimatization. So this is always the crucial altitude that people get sick. And then we trekked to the base camp. We stayed in base camp for acclimatization. And then we had a high camp at 5,600 meters. This is already a pretty high sleeping height. Then we went to the summit, 6,400 meters. We returned to the high camp, slept there again, and went back all to the base camp. And finally, the trek was continued and we were flying out. So here you can actually see the circle that's leading around Annapurna. So this is Besi Sahar. And then you are going in a circle around the Annapurna mountain range. Here's the Shulu group. The mountain just in behind. So if we look at the high altitude profile, we started more or less at sea level. Then we were going up all the way to 6,400 meters. Took about 15 days. And then there's also a nice pass that's called Torong La. and then we went back to sea level. So this was organized by the trekking team. It's a Nepali organization, and they are charging, for example, for 17 days trekking $615. You also need a climbing permit. This is $78 per person. And you also have to pay for the climbing guide equipment, $60. This is just a very nice opportunity for doing high altitude experiments. Highly recommended. And with that, I'm actually finishing my slides. Any questions? Manuel, who invited Mr. Guga? Actually, at this time, nobody wanted to speak, so I took the last slot of spring school. So invitation was by Guga himself. Thanks for staying so long. Arthur is asking, what biosensor products or sensoring devices are developed, sold by g.tec? Maybe I missed it, sorry, if you already addressed this info. A lot. So you will see it again tomorrow. There are a lot of different talks showing different devices. Fatima, yes, it's visible. Arthur, did you experience altitude sickness while EEG recording yourself during one of your trips? I'm curious about the outcomes and brain signal characteristics in this case. So I experienced once high altitude sickness when it was the first time in the Everest region in Nepal. And we were just carrying our own backpacks because Austrians believe that you have to carry everything yourself. It was pretty heavy, and then we were more or less running up the mountains, and we slept in Gora Shep. This is around 5,400 meters. So it was the first night above 5,000 meters, and then during the night I was waking up all the time, and I had really difficulties to breathe. So I started to sweat because it was so difficult. And one thing that you can do is you can sit the body up, and then it's easier to breathe. And of course, you can also do this auto beep respiration to bring more oxygen into your blood. So it's not a nice experience to suffer from high altitude sickness, but nowadays I'm smarter, so I'm not carrying so much, and we are going up slower. So on average, you should gain about 300 meters altitude per day so that you're not getting high altitude sickness. There's also some medication like Diamox, but there's a big debate if Diamox is actually helping. So the best thing that you can do is that you don't sleep higher than 300 meters more than the day before. Did you face more difficulties to bring this mobile EEG on the market compared to other products? This was actually pretty funny because when the first prototype of the mobile lab was finished, I was just jumping into the plane on the way to Nepal to do the recordings on the Shulu Far West. And then the programmer actually had a programming mistake inside the firmware. And this caused the mobile app to shut down every minute. So it took forever to run an experiment because we had to restart the software again and again. We came home, he fixed the bug, took him like 30 seconds, and it worked nicely. But important about the mobile app was that it was using standard AA batteries, and they are just performing very nicely at cold temperatures. So in the night, in the tent, we put the device into our sleeping bag to keep the batteries warm and to be able to run the experiments. This was especially important for the Pocket PC, which had a rechargeable battery, and this battery was very sensitive to cold temperatures. DB is asking, from your experience there, how cold your technology augment the body beside basic altitude training as an adaptation for extreme environment, sinking space, high zero G? Yeah, the devices, they survive nowadays a lot. So the lithium-ion batteries are much better than the older accumulators. So they can do minus 20 degrees Celsius, and they just lose a few percent. That's not really a big problem. High accelerations are also not really a problem. There's a company in Austria called Amst, and they build G simulators for the army and for pilots. And they speed it up to a couple of K, like 12 Gs, I think is the maximum, and the devices just survive that. Zero G is something that we are doing in Airbus zero G flights. I think there is also a lecture, or at least last year, Schilling gave a lecture about the zero G flights. This is no problem for our EEG and BCI hardware, but you have to be careful with the hard disks in computers. So hard disks have sometimes a hard time with zero G because they need some acceleration to read out, but you can use, of course, solid state disks for these environments. Can we record underwater? Of course, if you attach the device to your body and you are in a submarine or in a diving suit, that's no problem at all. With the wireless transmission, we just have a problem with water because we are using 2.4 gigahertz and it just doesn't go through water. So you need a cable if you want to have the recording system above. Maybe you remember last year, Matt was talking he did EEG recordings with dolphins. Was very interesting. You definitely had this one hidden under your sleeve. Many thanks. Of course, I have to hide something from Manuel. Laser, does high altitude sickness accumulate over time, or is it instantaneous? It accumulates, but nevertheless, it's pretty sudden that people feel really bad. So in Nepal, I was mentioning many people get sick at 3,500 meters when they sleep there. For example, Namche Bazaar is one of these villages. They have coffee shops, they have restaurants. So when people arrive, people are happy, they eat a lot, and then they go to sleep. And during the night, they wake up, they have a headache, they vomit, and they feel really bad. And this is the first time when it's becoming dangerous because there can be some problems in your lungs. They are filling with fluids and liquids, and then you cannot breathe anymore. But much more dangerous is a brain bleeding that can be produced by the high altitude sickness, high altitude cerebral edema, and this is life-threatening. So if you're getting that, then you have to go down as quick as possible, or you have to be treated immediately. Manuel, my reflection is, shouldn't climbers and altitude trackers use some BCI in case they need rescue and cortical brain equipment for control and monitor signals to prevent altitude sickness? Of course. So with the equipment that I showed you, it's very easy to manifest that the body and how much your body is already affected. But of course, it's difficult to carry all these things. So if you have in mind the symptoms like headache, not feeling healthy, balance problems when you're sitting down and standing up, and then you feel dizzy, these are the first signs. Then you can measure, of course, also oxygen saturation. And if you're counting all these things together, then you get a very nice idea what's actually going on. For neuroscience experiments, it's super interesting to look at the EEG because there's not much literature about it. And it's amazing how soon you can see that the EEG is affected. Remember, Dachstein is only 2,700 meters. So many people are bringing children to this altitude and nobody believes that the brain is already affected. And another very nice side effect is if you're recording on Kilimanjaro or in Nepal in the mountains, then there's no power line interference. You get really clean EEG data. Laser, by shrinking during sleep with cerebral spinal fluid increase flow to clean oxygen, radial and toxins. Could this be why having sleep situation? Of course, body is also coming to rest and then it hits you full speed. So Beide is asking, is adapting to height so different between people because of the heart rate? One of my friends felt dizzy in 1,500 meters when we were okay in 4,000 meters. This is highly individual. So in our climbing team, there's one guy who gets high altitude sickness almost all the time. So he even started to train already with a kind of oxygen chamber in Vienna because before we board to get used to the high altitude. And then he's also taking Diamox with him. But also personal fitness is of course important. So if you're fitter, if you're used to the high altitude mountaineering and all the exercise, then it's easier for you. But also people who never had problems at high altitude can suddenly get it. So it's a little bit difficult to predict. The nice thing is also when you are adapted to the high altitude, then you feel completely okay. And it lasts for about 2 weeks. So you get a nice boost by all the additional oxygen in your blood. Arthur is saying any characteristical brain signals or recognizable EEG patterns identified when altitude sickness compared to baseline. We just don't have enough data for that because in our teams, not so many people got high altitude sickness because we were always very careful not to get it, but it would be super interesting, of course, to do EEG recordings in these patients. So in Namche Bazaar in Nepal, for example, if you are located there and you're just waiting for trekkers and mountaineers who are sleeping there, you would complete the study within a few days because so many people are suffering there of high altitude sickness. Manuel, great pleasure, of course, that you're attending. Fatima, I'm amazed by the amount of courage, determination, effort, and of course the dedication of you and your team to carry out experimentation regarding neurotechnology. Actually, the doing BCI experiments in the mountains is more or less an excuse to go mountaineering. So it's just a very nice combination of pleasure with doing some neuroscience. And with that, I'm ending actually the lecture 5 minutes earlier than planned. Thank you very much for attending today. Tomorrow in the morning, I will let you know about the statistics again. Let's see how many people we had today. We are starting again at 8 o'clock Vienna time. Just use the same Zoom link. Thank you very much for attending such a long time and see you tomorrow. Bye-bye.